All right, so in matrix form, the three equations are as shown. So V, which would be this matrix, is equal to R, which is that matrix, times I. Yes, Mr. Brown?
So I was asking if you could briefly revisit the slide before this so I could verify something, please.
Pardon?
Could you please briefly revisit the slide before this?
Did you get the three equations?
Yes, sir.
Yeah, man. So it's just, yeah,
Sure.
that's just an interim. This is what I wanted to focus on from the three equations.
Sir, go to this slide before the previous one.
You know, I paused and asked if you had any issue with the equations. Nobody responded. I have moved on.
Sir, what?
Okay, so this is the matrix that we have before us. All right. So we have the voltages. We have the resistances. We have the currents. All right. So, Mr. Brown, what you would have had from the previous slide, we just showed that from equation 1. Let me just change the color here. From equation 1, these are the coefficients that we would have had.
Yes, sir.
From equation 2, these are the coefficients. And
from equation 3, the next row.
From equation 3, the lower one. So we now have a matrix equation based on the three equations. All right?
Yes, sir. Thank you.
Good. Okay. Of course, we can solve these equations or solve this matrix equation for I3. So that would be R inverse times V would give us I. Now, what I want us to do before we talk about solving the equation, I want us to look back or just to compare our matrix here, yes, with our general matrix. All right, where we have each element representing A11 through to A33. Okay, of course, the subscripts will be telling us the position of the element. So 1, 1 is telling us row 1, column 1. A33, the 3, 3 would be telling us row 3, column 3. Similarly, 3, 1 would be row 3, column 1, and so forth. All right, which is something that you would have already completed in math, right? So I don't need to rehash this. So this is our general matrix. And what I want to do now is to compare this matrix to the resistance matrix that we just looked at. So I just indicated that the subscript represents the position, row, and column. But we can also link this to the circuit that we just looked at. So let's do that. A32, yes, would represent the resistive element that lies between meshes 3 and 2. So A32 would represent the element between meshes 3 and 2. A21 would represent the element between meshes 2 and 1. All right, so let's take that. And then we look back at the circuit and make a determination as to whether or not what we are saying here is correct. All right, finish with this? Okay, so.
No, sir.
No, sir. Few more seconds.
All right, so here's our circuit. Remember we said that the element 3, 2 would have been between meshes 3 and 2. So this is mesh 3. Yes, that's mesh 3. That's mesh 2. The element that is between mesh 2 and 3 will be 4. All right. So if we go back to our mesh, our matrix, yes, the element between mesh 2 and 3, right? So 3, 2, A3, 2, row 3, column 2. So it will be 4. But of course, the element that is between 3 and 2 must also be the element between 2 and 3. So row 2, column 3, again 4. We also spoke about A2, 1, element between mesh 2 and 1. So let's go back to our circuit. Sorry, let me just go back to our circuit. All right, this is mesh 2, mesh 1. Element between mesh 2 and 1 is 6. So come back to our matrix. A2, 1, A2, 1, row 2, column 1, 6. But between 2, 1, would have the same element between 1, 2. So row 2, column 1 is also 6. All right. So we have spoken about, quote unquote, the off diagonal elements, but there are some other elements that we had there. For example, A11. A11, row 1, column 1, what that represents would be all the elements in mesh 1. What are the elements in mesh 1? 8 and 6, and that will give us 14. Yes? The element we just spoke about, this one between 1 and 2 would be 6. Yes? And so we'll get the 14, which is all the elements, yes, in mesh 1. This one would be between 1 and 2. Yep. And then, of course, the 0 would occur because there is no connection. There's no link between elements or meshes 1 and 3. All right, so mesh 1 is all the way over here, and it is separating, sorry, from mesh 3. So there's no physical connection, or there's no element linking, the two meshes. So that's where we get the 0 from. All right, so I go. And then we make the note here is that elements that are shared. So all the elements that are shared between meshes are negative. Or in other words, only the elements on the lead diagonal of the matrix are positive. Everything else is negative.
Wait, sir, can you read that once again, please?
It's written there. It's written on the screen. The elements shared between meshes are all negative. So the 6 was shared between meshes 1 and 2. Yes? So it's -6. Which means, therefore, that the element between 2 and 1 would also be -6.
Wait, so sir, is this a way where a person could determine if they made a mistake with the what do I say, the equations? Is that way it's like to say, all
Not
right, I made a
really.
mistake.
Not really. At this level, you don't have time to write the equations. So we are moving beyond you sitting down and writing equations. We are now at the place where we are going to look at the circuit and write the matrix. So it's not for checking. It's how you know approach mesh analysis going forward. Trust me, you'll see the benefit in a few minutes. So we repeat the process for the other 2 meshes. All right. So these 3 elements would therefore give us the second row. So between mesh 1 and 2, we have -6. Between mesh 2 and 3, we have -4. And then the sum of those 3 elements will give us the 26. For mesh 3, A33 would therefore be 12. Shared between the meshes would be 4, so we have -4. There's nothing linking 1 and 3, so it is 0. So that would be our resistance matrix. And of course, we can solve. And as before, we have our mesh equations, and we can do whatever we need to do, having found these answers. All right. So we have our currents. We can use them to analyze further our circuit. But of course, there's no point in you coming to Networks 2 and all we are doing is telling you of a better method to do what you already know to do, right? Because you all can do mesh analysis. So how does this help us? Simply put, if we apply this general principle to all circuits, whether we are looking at resistances or impedances, and of course, when we speak of impedances, we're talking about circuits containing reactive components. So whether I'm dealing with a circuit that is purely resistive, or I'm dealing with one that has inductive and capacitive elements, whether I'm dealing with a DC circuit or whether I'm dealing with an AC circuit. Yes, the principle that I've just outlined will be applicable. So instead of putting in resistors, I'm now putting in impedances. Yes, and based on what we have before us, we can then determine the impedance equation. Note, however, students, note carefully that in this matrix, I have included a fourth row, which means that we are writing everything on the, well, whichever side you want to put it. But let's say we are putting everything on the right-hand side. So the sources are over there too, which is what we have here. Now that is when it's in the matrix. So we are putting it in the matrix. So it means that all of this would be equal to 0. All right? Now, here is where it makes life even simpler. I want you to look at each mesh. Look at each mesh. Let's see now. Ms. Richards, for mesh 1, Delia Richards, for mesh 1, which terminal is the current entering? The source.
Terminal, sir, from bottom to top. That's what I mean.
Which terminal is the current I1 entering in mesh 1?
So I said from bottom to top.
Pardon me?
From the
No
dial.
terminal on the bottom, Ms. Richards. Come on.
Negative, sir. The negative
Pardon me?
terminal. The negative terminal.
The negative.
Negative.
Good. All right. And because of that note, we just write E1. Yep. We write E1 as minus E1. Similarly, for mesh 2, come Ms. Richards, we'll make sure so you understand what you were saying. For mesh 2, which terminal is the current I2 entering?
Mesh 2.
For the source in the mesh, which terminal is it entering? What's the source in mesh 2? Mr. Richard,
Yes, sir.
what's the source you see in mesh 2?
Sir, the E2.
So which terminal is the mesh 2 current entering?
Negative, sir.
Negative. So we put another negative, seat up the sum. All right. Don't move. What source are sources in mesh 3?
There are two sources, the E2
Yeah,
and
what
the
them name?
E3, sir.
Huh?
E2, the E2 source and the E3 source.
Okay, which terminal
Yes, sir.
is I3 entering?
I3. Sir, the two of them?
Which terminal is I3
Oh, the
entering?
negative.
Stop guessing. Look at the circuit. If it's entering the negative for 1 and 2, and it's coming at the bottom of the arrow, does I3 look like it's coming into the bottom of the arrow? Huh?
No, sir, it's going to the opposite.
Okay, so which
direction.
terminal is it entering?
The
Huh?
positive, because it's the positive
The
terminal,
positive.
because
So it's
going
entering the
opposite
positive terminal, which is why we have E2 plus E3. All right, so the sign assigned to the source, yes, in each mesh is based on the terminal entered by the particular mesh current. So in mesh 1, it's going into the negative. So we have negative E1. For E2, it's entering the negative. So we have minus E2. For mesh 3, it's entering the positive of mesh of supply E3 and the positive of E2, positive of E3. So we have 2 plus 3. Okay? Everybody clear on that?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
All
Sir,
right.
can you repeat that, sir?
So it's written. Honestly, we can't repeat it. Tell me what you don't understand. It's written right there. You know. Tell me what you don't understand. And let me explain it.
All right, sir. Looking at the circuit where for mesh 1, the arrow going up at E1. So I was thinking
I don't want to know what you're thinking. Look at the statement I have written. Look at the statement. What does it say?
note that the sign assigned to the source are based on the terminal entered by the particular mesh current.
What is the mesh current over mesh 1?
I1, sir.
Which terminal is it entering?
Sir, it would be entering. Sir, that's a AC circuit. AC
Which
source,
terminal is it entering? If you want to call it AC, all right, live and neutral. Which one is it entering?
Sir, I'm saying it's negative, sir.
Pardon me?
Negative, sir.
Okay, so problem solved. So we put minus E1. That's all we're saying.
Okay.
So go ahead for me. Write the matrix equation, including. So write the matrix, including the source. So do that for me quickly.
So you can go back to the previous slide.
All right. So let's see now. So Beckford. Mr. Beckford. Should I assume that Mr. Beckford isn't in the room? Or just has his name here? Folks, I haven't changed him. So Mr. Beckford not in the room, but posting that he's here, I will remove him. Mr. Morrison? David?
Yes, sir.
All right, give me the first row, please.
Sir, I'm not finished yet, you know, to
Huh?
get up from. I never started, sir, to get up from the next while ago. Sorry about that.
All right, no man, it's all right. You're online, so stay there. Let's work on it. First row. How you find the first element? What will be A11?
We are asking.
Hold on. Would be the first element in the first row, first column, sir.
Yeah, but how we find it? What are we looking for? All right, somebody want to help me? Somebody.
Would
Dean.
Go ahead,
So-
Mr. Hodges.
So that would be all of the elements.
So you would add all the elements in mesh 1, which is
Which
the
would do what?
5 plus 6 minus J4. ohms.
which gives you?
11 minus 4 J4.
Okay, all right, so that's A11. What will be A12?
A12 is the elements that is shared between mesh 1 and 2, which is the 6 minus 4J.
Okay, so what would that be?
Negative 6 minus 4J.
So that will be minus 6 plus J4.
It's a capacitance there, sir.
Yeah, man, I know, but it's the negative of it.
Oh,
So
yes,
it's
yes,
minus 6 plus J4.
yes, sir, yes, sir, yes, sir, yes, sir.
All right. So if that is A12, what is A21?
A21 is 6 plus J4.
Minus 6 plus J4, it will be the same.
Yeah.
It's all right. Don't beat up yourself, you know. This is how we're going to get there. All right. Now for the go back to mesh 1.
Source
For the source, what would that be equal to?
is entering the negative, so it's a negative 100.
Beautiful. All right. Thank you, Mr. Hodges. Ms. Campbell?
Afternoon, sir.
What do you do? Give me the second row.
Sir, second row would be minus 6 plus J4, 10 plus J3, and 0.
10 plus what?
Plus J3.
10 plus J3?
Remember the capacitance.
I'm not agree with you.
Oh, I didn't remember the capacitor. So
All right, so add them up now.
so that would be 3 minus 4 minus 1. 10 minus J1 then.
10 minus J. All right. So row 1. All right. So we'll have 11 minus J4 into I1 minus 6 minus or negative of 6 minus J4 and then minus 100. And then for row 2, as was just said, we have, so this and this will be the same. Okay. And so we can put that. So this would be our matrix. Fair enough? Now, we can use different methods. So, of course, I have given you the option to use your calculators. Nothing wrong with that, continue to use it. But of course, I also have to introduce you to using Kramer's rule in solving this. And so for Kramer's rule, we'd have I1, and all we do in applying Kramer's rule is to block out the particular column. Yes? And then write the rest of the matrix. So if we blocked out column 1, which would be representing I1, we'd have I1, yes, over the determinant of the rest of the elements, which in this case, rest of the elements.
Here what we are going to do, or at least what me are going to do.
All right, we hear what you're going to do.
Focus in a class, when we talk, take picture upon whatever.
Miss Campbell, you may want to mute.
Oh, sorry, Jesus Christ.
Yeah, I think you want to mute, especially now. All right. Thankfully, he's off the cross. But anyway, so we have I1 over the modulus of what remains, and then minus I2, yes, over this and that, and then 1. So we block out for the 1. We block out this column, and we have the modulus, or the determinant, sorry, the determinant of the other elements. Yep. All right. And then from this would be a constant. So we'd have these values from which would give us I1 and I2. All right. So again, if you wish, you can use your calculators to solve this, or depending on what we ask, yep, you can use Cramer's rule as shown. Any questions so far? All right, moving right along. So I1.
Sorry, before we move, are you saying that in a test you might ask us to use Cramer's rule or our calculator?
Pardon me?
Are you saying that in a test you might ask us to use?
I can ask you to do anything in an assessment, as long as it is covered in the syllabus. Anything whatsoever. Once I have taught it, it means that it is up for assessment.
Sir, that's not what he was asking.
Pardon me?
That's not what he was asking. He was
You're asking if could you ask him to use Cramer's rule?
No, sir, that wasn't the question. He was asking if he could use a calculator or just use it by hand.
And I'm saying I can ask you to do anything once it's on the syllabus. So even though you have that option, I can also ask you to use Cramer's rule. So my answer is consistent with the question asked.
Okay.
And Cramer's rule is on the syllabus.
Sir, could you go back to the previous slide?
All right, so I1, that's the answer. I2, that's the answer. We're not going to spend time in this session looking at how we'll apply the currents. We have spent a lot of time doing that in networks one. So whether we are finding power or voltage drop across elements, that sort of thing, apparent power, active power, you name it. We can ask you all of that. What we're interested in is just how we go about analyzing our circuits, setting up our equations, and simplifying our equations. What we will not do for this particular area of application is to use the dependent sources, all right? Because that takes a little more work. And then again, yeah, we might use them, but let us see how we proceed. So here you have another circuit. Please go ahead and form the equations, the matrix equation for me, please. All right. Anybody want to volunteer?
Yes, sir.
Go ahead, Mr. Marsh.
All right, sir. So for the first row, I have 60 minus 40, 0, minus 100, angle 0.
Okay, go ahead.
For the second row, I have minus 40, 40, minus J25, and 0. And for the third row, I have 0, minus J25, 10 minus J25, and minus 100, angle 0.
All right. So you're
positive.
almost.
Positive. Sir, the last one is positive. The last one is positive, sir.
Right.
Positive
100. You're almost 100% correct. Anybody want, Mr. Brian, you raise your hand to correct him?
Yes, sir. I wanted to challenge, well, this one specifically I picked out. The element between mesh 2 and 3. The element between mesh 2 and 3. He he said it was in the matrix, it's minus J25, but I think it's actually positive J25.
Yeah, that's the error, Mr. Marsh.
Yeah,
It's
agreed.
J25. All right, because remember, this is minus J25. So it's a negative of the negative, which will give you J25.
All right, thank you, sir.
All right. So in terms of the solution, as I said, we can either focus on you using Kramer's, or depending on what we're asking, then you just simply go ahead, plug this into your calculators and churn out a response. All right, and then apply it. All righty.
Sir, just a moment, sir. I think I have some. For mesh one, for the first equation, isn't the current mesh one entering the negative terminal?
Yes.
Oh, I wrote it inside the one mesh.
If it's inside, then it will be minus.
Yeah, sorry. Yeah.
So why are you sorry? You're correct.
Yes, sir.
Nothing to be sorry about. All right, so that's for mesh analysis. So we have we can now form our equations, but just by looking at the circuit, we can write the matrix, solve it, and we're good. All right? Of course, as I said, the other activities, whether it is to find power, you name it, those things, you will treat with accordingly. So, nodal analysis. So just now we were looking at, for the mesh analysis, the elements within the matrices, we determine them by looking at those contained in the mesh being considered and the corresponding voltage within the mesh. For nodal analysis, yes, we're going to now look at the reciprocal of the element and the corresponding current which flows. Yes. In mesh analysis, for the diagonal elements, we're looking at the sum of the elements within a mesh. For nodal analysis, we're going to be looking at the sum of the reciprocals of the elements connected to the node. In other words, if you know mesh analysis, you automatically will know nodal analysis. To be fair though, it is not as simple, but doable. So let us see how we do that. Take the circuit, please. And for the two nodes that we have here, if we were to use conventional nodal analysis, then these are the equations that we would have. From these equations, yes, we can write the matrix showing our admittances, which of course would be the reciprocal of our impedances, yes. We can write the matrix expression. Right. So this would be our admittance. So it's V times Y times V to give us I. We're going to say a couple of things about how we determine I. If you look back at the circuit, you'll see that for the 30 volt source, we're dividing by 20. For the 15, we're dividing by 10. So it's 30 over 20, 15 over 10. So we're simply dividing by the resistance that is in the same path as the source. All right. So here we would have just simply rearranged our equations and we would have found V1 and V2.
Sir,
Yes.
sir, could you show you got the values for V1 and V2? Did you use simultaneous equations?
I just use the matrix equation. So I found the inverse of this and pre-multiplied it by that. So I took this over. So I found the inverse multiplied by the current to get V1 and V2. Just use matrices.
Okay.
All right. So let's just look back at our equation or look back at our circuit and see how we would go about forming our matrix equation. So let's start with node 1. Let's start with node 1. All right? For node 1, so black code. So Brian, you still have your hand up or that was from before?
That was from before, sir. Apologies.
All right, so Mr. Blackwood?
Yes, sir.
All right. What are the elements connected to node 1? Tell me the resistive elements connected to node 1.
And the 20 ohm, the 4 ohm, and the 5 ohm.
All right. So A11, as we said, A11 would just be the reciprocal, the sum of the reciprocals for each of those elements, which would be that. Next, we have 2 nodes. So what size matrix would we be dealing with?
2 by 2.
2 by 2, good. So what's the element between nodes 1 and 2?
The 5 ohm.
5. So we have minus 1 over 5. And of course, if it is between 1 and 2, it is also between 2 and 1.
2 and 1.
So in other words, students, the matrix that you form must be symmetrical about the leading diagonal. The only time it will not be symmetrical is when you have a dependent source involved. But as I said, we muddied water just now with dependent sources. Continuing with you, Mr. Blackwood, for node 2, The elements connected to node 2?
The 5 ohm, 10 ohm, and the 2 ohm.
And these are the reciprocals.
Yes, sir.
All right. So that's our matrix.
You see, Mr. For on the previous slide where you have -14, negative V2, and you had
Where I have what?
but the previous slide where you had -42, negative V2, and you asked him, I don't know what the question I asked him, where you said 1/5. What was the question I asked him?
Where I had negative what?
Where you asked him, I don't know the question I asked him exactly, but he said 5. I think it was the
I asked him the element between nodes 1 and 2.
and that's the reciprocal of the element. Okay.
So you get -1/5.
And minus because it's all right. So
Same principle as before. All the off diagonal elements are negative.
all right, thanks, sir.
Okay. And I also indicated that for the source, for the currents, it would be 30/20, 15/10. Any other question? No? All right. So I have one for you.
Sir, I'm just not clear with the last part in determining voltage. Or would you follow a similar procedure for using this method?
Don't understand the question, Mr. Thompson.
Yes, sir. I'm saying that I wasn't following the last part of the procedure, sir.
What procedure?
In using the matrices to determine the row and column elements.
All right, let's deal with this one. So for this circuit that we have before us, still with you, Mr. Thompson. For this circuit, what size matrix are we going to be operating with?
So 3 by 3.
Why 3 by 3?
Well, there are, no. So I like to check, sir, it would be 2 because there are 2 nodes.
Okay, so it's a 2 by 2. It's a 2 by 2.
Yes, sir.
Good. So for position A11, what are the elements connected to node 1?
The 20 ohms, the 40 ohms resistor, and the 15 ohms inductor.
Okay, and what did we say about, for nodal analysis, what did we say about A11? What are we going to use to find out?
You said that you would find the reciprocal of the sum of the shared element.
No, that's not what we said. We said we find the sum of the reciprocals.
Oh, yes, sir.
Right? So it's not the reciprocal of the sum. It's a sum of the reciprocals. So what's the reciprocal of 20, 40, J15?
So I didn't hear that, sir.
What's the sum of reciprocals of 20, 40, and J15?
It would be 1/20 plus 1/40 plus 1/15.
1/J15.
Yes, yes, sir.
All right. And what would be A12? What would A12 be equal to?
It would be the inductor, J15, 1 over J15.
Sure about that?
Negative 1 over
Okay, so it's a negative of 1 over J15. And 2, 1 would be the same, eh?
Yes.
All right, so we're all right, man. So write the matrix equation for me. Let me go before we go. For node 1, what will be the current?
It would be 100 over 20.
All right. So all right, man. So write the matrix equation. Yes, Mr. Humphrey.
Yes, sir. Just one question. The symmetry, the 2 by 2 matrix will be symmetric. Will always be symmetric, right?
The matrix will always be symmetric. Whether 2 by 2 symmetrical, whether 2 by 2, 3 by 3, 4 by 4.
Okay, that was what I was going to. If you have bigger matrix, will it still be? Okay, all right, sir.
Got to reach a solution.
Yes, sir.
All right, Mr. Marsh. Let's confirm your equations. Does that look familiar?
Yes, sir.
Okay. So what did you get for V1 and 2?
So for V1, I got 27.8161, angle minus 28.47 degrees. And for V2, I got 86.8947 with an angle of 14.51 degrees.
All right. Let's see. Let's see. Oops, sorry. Still looking for me there?
No, sir. I think I did not put the J. There was a J on the 100. I didn't put the J on the 100. I see you have a J. I see you have a J on the 100 over 10.
Because it was 100 at 90.
Yes, sir. So I made a mistake right there, sir.
Okay. All right. So correct that for me.
All right, sir.
Sir, just some clarity here for position A22, where we're supposed to sum up all the elements that is connected to V2.
Node
Reciprocal
2,
rather,
node 2.
or node 2 rather. So I have 1 over, isn't the inductor value just 1 over R J over 15? Why is it a negative?
Go again.
The inductance value that you have here, which is the J15, right? The reciprocal, is it just 1 over J, 1 over J15, or 1 over, yeah, positive rather? Isn't it supposed to be a positive number?
All right, multiply by 1, which is J over J. If you're querying how I move from here to here?
No, sir, not that one, sir.
Which one?
Position A22 or node 2, the one you have in bracket down here. Oh, you have it.
Yes, sir. I believe it's
Oh,
same
it's there.
concept he's asking about.
Oh, it's there.
What you're
Okay.
talking about?
Yeah, I didn't look on the one you had top. It's there. I just noticed. Okay.
All right.
Okay. All right.
You have to just
Sir,
you have to be careful with the signs, eh?
yes, sir. Explain the one you were going to explain with the negative 1 over J15 to the J over the 15.
I'm saying multiply it by 1, but represent the 1 as J over J.
All right. So J.
Make sense now?
Yes, sir.
Now I'm allowing you to do this because what you're actually doing is, please for a better word, ferreting out some of the errors that will come up in this type of analysis. By the way, it is now 4 minutes to 3. I don't know how many of you signed up for the class after this. But anyway, I'll just work through to the end of this question, and then we will see where we go from there.
Question, sir.
Sir, I have another class now.
Hey, sure you can.
But I would watch the recording. All right then, sir.
So we go through this tomorrow in the next class, huh? Yeah. We'll go through it again tomorrow. So those who need to leave, please do. Yes, question.
All right, sir. So for V2, where you had J100 over 10, I know that you multiply, you divide the voltage by the resistance, so like the 100 over 20, I understand that. But for the next one, how did you get J100 over 10?
It's 100 J9, it's 100 at 90 degrees.
90.
You're converting from polar to rectangular. All right, Mr. Facing?
I think I get what you're saying, sir.
Sir,
Yes.
will you be going over how you found the final answer? So in terms of the 5 of J10 matrix times 120, 150.
I'm not understanding that.
Sir, that the last part, I got I
You
figured
mean
out
why
how
am
you-
I multiplying by the 120 over 150?
Yes, sir.
I'm just trying to get rid of the fractions. Remember, if you multiply in a matrix, if you multiply a row by a number, you're not going to change the result. Remember that row would represent a single equation. So if you multiply every element in an equation by a constant, would you have changed the balance of the equation?
No, sir.
All right. So you can multiply it by 60 if you wish, or 600, it doesn't really matter. But I have chosen 120 for the top row, and I've chosen 150 for the bottom row. But let me ask, is there anybody else who is unclear about what we have up to this point? All right, so if you're not unclear, good. When we multiply Mr. Thompson by 120, the top row would now become 9 minus J8, and we have J8. So if I multiply 120 by that, yes, 120 over 40 is 3. So you go. Mr. Thompson? Sorry about that. My internet is a bit unstable. We'll proceed. So I was asking, is everybody clear up to this point? Yes, no, maybe so.
Sir, could you, I'm not sure if I'm having some difficulty hearing what you're saying, sir.
I said I know my internet went just now, so I'm asking if you have a difficulty up to this point. Up to this point.
Sir, we cannot hear anything you're saying.
Is that any better? So the gremlins are here. Are you hearing me now?
Yes.
Yes, sir.
All right, let us see how best we can wrap this without losing out again. All right, so here we go. So I'm saying, if you are good with up to that point, up to this point, yes, then if you multiply the top row by 120, you would have 3 over 40 times 120. 120 over 40 gives you 333 is 9. 120 over 15 gives you 8. If you come to the bottom, 150 over 15 is 10. 150 over 10 is 15. And so this would be 40 here. So you do that calculation and you'll get that as your matrix. Are you clear now, Mr. Thompson?
Yes, sir. You multiply the entire equation by this.
Yes.
Okay.
And so in solving, this is what we get.
Sir, I still haven't gotten the understanding of the how you move from the, how you determine the V1 and V2.
Mr. Thompson, you know me not teach maths, right? You find the inverse of this and multiply it by this.
Oh, yes, sir.
Okay, if you bring this over here, so it will become Z inverse. But you would not have this times Z inverse because this is a 2 by 1. This is a 2 by 2. So of course you can't multiply them like that. So it will be Z inverse times the 600 J 1500.
Yes, sir.
So please go ahead, gentlemen, and find the voltages. Calculate it for yourself.
So is there like following this procedure, is there like a specific method you have to use to get the voltages? Because I know to get the inverse, you can find the adjoint and multiply by the.
Mr. Thompson, I'm not going to help you with the maths. You have to go check down at the maths department. I can't help you. I don't know how to simplify it. You have a matrix equation, you find the inverse of one matrix and you multiply it by the other one. I don't know how else to simplify it.
Okay,
this is something that you would have covered. That's why there are prerequisites for this module. And one of them, I believe, is Math 2 or Math 3, along with Networks 1. But of course, you would have needed that for Networks 1 anyway. So I can't go back on this. Sorry.
So it is not requisite to give all the work in this.
All right. So has anyone confirmed the voltages?
It keeps chipping for me, so.
It's all going to be chopped up. I'm not sure how we're going to put all of this together. So we have the 15, we have the 40, we have the 20. We also have for the 25 and the 10. All right, so take this down quickly. All right. For the 25 ohm and for the 10 ohm. So these are the currents in each of the branches. Can I proceed?
Yes, sir.
All right. So now that we have the current in each branch, we now need to look to the power. And I'm going through this because, you know, yes, you're going to see it again. You're going to see this again. So for current I1 leaving source S1, yes, that would be the same current, that would be the same current leaving the 20 volt source, or rather flowing through the 20 ohm resistance. Yep. And note we're looking at the current leaving the source. Remember the current through the 20 was moving from node 1 towards the source because we had V1 minus V source, okay? So now we're looking at the current leaving the source, so it will be the negative of what you had calculated.
So repeat that, please. It will be the negative.
The current from through the 20 is V1 minus 100 over, is
20.
V1 minus 100 over 20. But we are looking at the current leaving the source. So it obviously be going in the opposite direction.
Understood, sir.
So I'm saying that's why it is the negative of the I-20 current. Similarly for the current leaving source 2, that would be the current through the 10 ohm resistor. Again, it's the negative of the current we calculated. So note, you're finding the power being supplied by the sources. So if the current is being, if the power is being supplied, so if the power is being supplied, we are then looking for the current leaving. All right. So once we have that, then we know that S is equal to VI conjugate. So S1 is given by 100 plus J0 times the conjugate. So the key here, students, is that first, you are looking for the current leaving. However that affects the signs for the current, it's neither here nor there. In the case of the second one, you get a minus real and a positive imaginary. For the first one, it was a positive real and a negative imaginary. Now that you have done that, you then find the conjugate, which means that you're only going to be adjusting the imaginary part. And having done that, you now have S, which is in the form P plus JQ. P plus JQ. So what this is saying to us is that one source is actually delivering reactive power, while the other one is absorbing reactive power. And we are going to now confirm that. So in terms of the question that I asked us about the total active power in the circuit, which would simply be the sum of these two. So once we have done that, right? So that's our P. So that's one approach. But let us say you weren't too keen on that. We know that active power is dissipated in the resistive part of the circuit. So what we find are the modulus for each current, and square them and multiply them by the resistances through which they pass. And we see that we get the same. So we get the 574 in both instances.
Sir, you can go back to the previous slide.
What about the previous slide, sir?
I didn't get to record the S2 equation.
It is V times I conjugate. V0 minus J100. And you have the current already. So we have our I squared R, I squared R, I squared R. Note, I am not multiplying it by the inductance that we have in the circuit or the capacitance, because those would represent reactive power. So I'm only looking at the active power, so it will be the 20, the 40, and the 10. We add them, and of course, we get the
Total active power.
The active power dissipated. All right. In closing this afternoon, take this question for me and do it in preparation for next class, for the next lecture class.